Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Fancy Counting and Such. As always, I encourage you to be an active learner while watching these videos. So we're going to talk about counting techniques, and we're going to talk about the general multiplication rule. We're going to talk about permutations, combinations. Here order matters, here order doesn't matter, and special cases where we have non-distinct items and we're using these to compute probabilities. So we're combining several concepts when we're doing this. By way of introduction, let's consider working towards the multiplication rule. Suppose you're going to a restaurant and it's a fixed price dinner, and for an appetizer you can choose soup or salad, and for the entree you can choose baked chicken, broiled beef patty, baby beef liver, and roast beef au jus, and for dessert ice cream or cheesecake. How many different meals could be ordered? Well, we're going to just look at a tree. So you can start with your appetizer, and either you will take soup or salad. And then for each of those, you could have 4 different meat entrees and 2 different desserts. So if you build this tree out of all the possibilities, you see that there are a lot of possibilities that can happen. 1, 2, 3, 4, 5, 6, 7, 8, 16 different possibilities, which is 2 times 4 times 2. So you see we're multiplying at each stage by the number. Now this motivates what we call the multiplication rule of counting. If a task consists of a sequence of choices, just like I will choose my appetizer, I will choose my entree, and I'll choose my dessert. So a sequence of tasks is a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on. Then the task of making these selections can be done in, just multiply all these things together in that many different ways. Here's an example. Now in this one, repetition is allowed. So you see airports have names. For example, O'Hare is ORD, and Midway I think is MDW. I don't fly as much anymore as I once did. But Fort Lauderdale is FLL. So you see this administration group assigns 3-letter codes to airport locations. And they do this to make sure that communications are crisp. You don't say I'm going to O'Hare, it's ORD. For baggage and other things, these are used as well. And this is the code for Fort Lauderdale, FLL. So you see that letters can be repeated. How many different airport codes are possible? Well, you can think about there's 3 spaces, and you can put a letter in each one of them. So you can put 26 here, and then you could, for every one of those, you can put 26 different ones here and 26 different ones here. That is 26 cubed, and that's well over 17,000 different airport codes are possible. Sometimes you have to count without repetition. For example, here's the problem. There are 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, the second person is the vice chair, and the third is the secretary. How many different committee structures are possible? And here you have 1 person in each office. So you can put 3, think about them as being chairs or little lines here. There's the president, and you pick them first. So there's 14 different ways you can choose the president. And then there's 13 ways you can choose the vice chair, I guess it's called. And there's 12 ways that you can choose the secretary. So by the multiplication rule, you multiply these together and you get a little better than 2,000 different committee structures are possible. So let's do a problem. A man has 6 shirts and 4 ties. Assuming they all match, some guys would not care, but assume that they all match. How many different shirt and tie combinations can he wear? You know what to do. Let's see how you did. Well, we just use the multiplication rule. There are 6 shirts and 4 ties. So 6 times 4 equal 24 different combinations, different wardrobes the man can wear. We introduce some notation now because you see we're multiplying a lot of numbers together. This helps us do it more concisely. If n is greater than or equal to 0 as an integer, that means it is 0, 1, 2, 3, dot, 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 and so on and so forth. Then the factorial symbol, that's what you call this, is factorial. When you read this, you say n factorial. And that looks like an exclamation point, but it follows the n. It's not a punctuation mark here, though. It's a mathematical symbol. And it's defined as follows. N factorial is you start at 1 times 2 times 3, dot, 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 keep multiplying till you get up to n. So that is n factorial. 1 factorial is 1 because you're just multiplying 1 by itself. And 0 factorial is how many ways can you do nothing? And there's only one way, so that is 0 factorial is 1. So, for example, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. And this table lists the values of n factorial for n between 0 and 6. Notice that factorials grow very fast. We showed you a video where you saw that exponential growth really trumps linear growth. Factorial growth way trumps even exponential growth. So let's talk about another example. This is called the traveling salesman problem. Suppose you've just been hired as a book representative for Pearson Education. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? Well, you call the schools A, B, C, all the way up through G. That's 7. And you can think about the ways that you can visit them. So there are 7 ways you can visit the first school. And once you visited there, you don't have to go again. So there's 6 times 5 times 4 times 3 times 2 times 1. 7 factorial, there are over 5,000 different routes possible here. One of the problems they ask you to try is 5 factorial. You know what to do. Let's see how you did. So 5 factorial is 1 times 2 times 3 times 4 times 5, and that is 120. And actually, since multiplication is commutative, most people would have said 5 times 4 times 3 times 2 times 1, starting with the highest number. That actually might be a better way for me to be saying it. Let's do another word problem then. So suppose Dan is going to upload 12 songs into his digital music player. In how many ways can the songs be played without repetition? Can the 12 songs be played? You know what to do. Let's see how you did. And we'll see how you did when we continue in 8.1.